Welcome to the AstroGuy Podcast. I'm your host, Wayne Zuhl. In this episode, we're diving into one of the most exciting astronomical projects of the 21st century, the Vera Rubin Observatory. If you're someone who loves deep sky objects, long-term surveys, and massive data sets, or you just want to learn more about how astronomers are studying the universe in unprecedented detail, then this episode is for you. We're going to look at what makes this observatory unique, what the LSST, the Legacy Survey of Space and Time, is all about, and why the data it collects could completely transform our understanding of the cosmos. So let's get into it. Before we talk about the telescope that bears her name, we need to take a moment to talk about the extraordinary person behind it, Dr. Vera Rubin. Vera Rubin was a pioneer, not just in astronomy, but in the fight for equality, especially in science. She was born in 1928 in Philadelphia and grew up in Washington, D.C., where she first became fascinated by the stars as a young girl. Her parents encouraged her curiosity, even though at the time astronomy, and science in general, was very much a male-dominated field. She earned her undergraduate degree from Vassar College in 1948, which was one of the few institutions at that time that accepted women in the sciences. From there, she applied to Princeton for graduate school, but she was rejected, not because she lacked credentials, but because Princeton simply didn't admit women into their astronomy program until 1975. So instead, Rubin went to Cornell, where she earned her master's degree. She later earned her PhD in 1954 from Georgetown University, and this is where her story really starts to shift from inspiring to groundbreaking. Vera Rubin is best known for her revolutionary work on galaxy rotation curves. In the 1970s, she and her colleague Kent Ford used spectroscopic observations to measure how fast stars orbit around the centers of spiral galaxies. Based on Newtonian physics and what we could see, the visible stars and gas, those outer stars should have been moving much slower than those near the core. But Rubin found that they weren't. They were moving just as fast, or in some cases, even faster. This wasn't just a slight discrepancy. It was a huge gap between what theory predicted and what the data showed. The only explanation that made sense was that there was far more mass in those galaxies than what we could actually see. Something invisible, something massive, something that didn't emit light. That something came to be known as dark matter. Now, Rubin didn't discover dark matter. Fritz Zwicky had proposed the idea decades earlier, but her careful, consistent, and convincing observational work gave it the strong scientific footing it had previously lacked. Her galaxy rotation curves became some of the most compelling and widely cited evidence for dark matter, and even today, her data is still being used and built upon in ongoing cosmological research. But Rubin's legacy isn't just about what she found, it's also about how she worked. She was known for being generous with her time, supportive of young scientists, and fiercely committed to inclusion and equality. She once famously said, "There is no scientific problem that a man can solve that a woman cannot." She was also a mother of four and often spoke about balancing her family life with her research career, a topic that wasn't widely discussed at the time, but one that resonates with many scientists today. Her life wasn't easy. She had to work harder than most of her male counterparts to be taken seriously, but she did it with grace, perseverance, and brilliance. And though her work helped fundamentally reshape modern astrophysics, Vera Rubin never won a Nobel Prize, something that many in the field still consider a major oversight. However, in 2020, she received a different kind of recognition. The Large Synoptic Survey Telescope was renamed the Vera Rubin Observatory, becoming the first U.S. national observatory to be named after a woman, and, frankly, there couldn't be a more fitting namesake. This observatory is about discovery, about pushing boundaries, and about looking deeper into the universe than ever before. That's exactly what Vera Rubin did her entire life, and now with this incredible telescope, her legacy will continue to inspire future generations of astronomers and scientists all over the world. So now we know about the incredible woman behind the name, let's talk about the observatory itself, because the Vera Rubin Observatory is no ordinary telescope. Located in the Chilean Andes on Cerro Pachón at almost 30 degrees south latitude, the Rubin Observatory sits at an altitude of 8,900 feet, high above much of the Earth's atmosphere, where the air is thin and dry and the skies are incredibly clear. This location was chosen very carefully. You want dark skies, stable air, and lots of cloud-free nights if you're planning to do serious deep sky imaging. And this site checks all the boxes. But what really sets the Rubin Observatory apart from other major observatories is its mission and design. This isn't a telescope built to zoom in on individual stars or galaxies and study them in depth like the James Webb Space Telescope or even Mount Palomar. This is a survey telescope, which means it's designed to scan huge swaths of the sky very quickly and repeatedly at many different wavelengths. In fact, it's going to do something no telescope has ever done before. It will image the entire visible sky from its location every few nights for an entire decade. That is mind-blowing. And it's possible thanks to a revolutionary combination of hardware and software. Let's talk about hardware first. At the heart of the Rubin Observatory is a truly unique optical design. It uses a special 3-mirror configuration that gives it an exceptionally wide field of view without sacrificing image quality. The telescope's primary mirror is 8.4 meters across. That's nearly 28 feet wide. The light the primary mirror collects is then fed into the largest digital camera ever built for astronomy. The LSST camera features a 3.2 gigapixel sensor. Let me say that again, 3.2 gigapixels. That's more than 3,000 megapixels. To put that in perspective, the camera sensor in your average smartphone is between 12 and 50 megapixels. Rubin's camera is more than 60,000 times more sensitive. And each image that it captures will be so large and detailed that you'd need 1,500 high-definition TV screens to display just one frame at full resolution. And it's not just the size of the images, it's how fast it takes them. The Rubin Observatory can capture an entire 3.5 degree wide patch of sky in a single 15-second exposure. That's roughly the size of 7 full moons side by side. And then it moves on to the next patch, and the next, and the next. Over the course of a single night, it can image 10,000 square degrees of sky, nearly a quarter of the entire celestial sphere. By the end of its 10-year study, the Rubin Observatory will have collected about 60 petabytes of raw data. That's roughly the equivalent of over 100 million DVDs worth of images. This is big data astronomy on a scale that we've never seen before. And here's the really exciting part. Just a few days prior to recording this, we got our first real taste of what this powerhouse is capable of. The Rubin Observatory has released its first light images from the LSST camera, and they are absolutely stunning. These are not just test frames, they're beautifully detailed wide-field images that showcase the telescope's incredible resolution and field of view. One of the first major images released by the Vera Rubin Observatory is being called the Cosmic Treasure Chest, and once you see it, you'll understand why. This single image contains more than 10 million galaxies. Let that sink in. That's over 10 million individual galaxies, each potentially home to billions of stars, all captured in just one small portion of the sky. The image focuses on the southern region of the Virgo cluster, one of the most massive galaxy clusters in the nearby universe. The largest and brightest galaxy in the image is Messier 49, a giant elliptical galaxy that sits at the heart of the cluster. But what's truly staggering is how dense this field is. Galaxies seem to fill every part of the image, and this is just a preview. These 10 million galaxies represent a mere 0.05% of the approximately 20 billion galaxies that the Rubin Observatory is expected to detect over the next decade as part of LSST. The full image spans about 25 square degrees. To put that in perspective, that's roughly 125 times the size of the full moon. It's not a single shot, but a mosaic built from 1,185 individual exposures, each precisely aligned and stacked to form this ultra-deep view. Multiple exposures were taken using different optical filters, allowing astronomers to isolate light across specific bands of the electromagnetic spectrum, from ultraviolet through the visible range and into the near infrared. This approach helps astronomers tease out important details about the age, composition, and distance of the galaxies in the field. And here's what's really impressive. All of this data, those 1,185 exposures, were captured over the course of just 7 nights. That's the power and efficiency of Rubin's 3.2 gigapixel camera system and rapid sky scanning capabilities. This image is not only visually stunning, it's scientifically rich, a first glimpse of the transformational data that Rubin will be delivering night after night. Another incredible first light image is this wide-field view of the Trifid and Lagoon Nebula, two of the most iconic star-forming regions in the summer sky. This image isn't just beautiful, it's a technical achievement that shows how fast, deep, and detailed Rubin's view of the universe really is. This composite was built from 678 individual exposures, taken over just 7.2 hours. When stitched together, they cover a patch of sky nearly 5 degrees wide by almost 3 degrees tall. The final result? A razor-sharp image packed with intricate detail, revealing the complex structure of both nebula in new ways. Between the dusty dark lanes of the Trifid and the glowing stellar nurseries of the lagoon, this mosaic is absolutely packed with texture and contrast. The Trifid Nebula, which we discussed in the What's Up in the July 2025 Skies episode, is located about 5,000 light-years away and is famous for its 3-lobed shape created by dark dust clouds. It features brilliant blue reflection regions and bright pink emission gases, evidence of active star formation. Just below it sits the Lagoon Nebula, a rich star-forming region about 4,000 light-years from Earth. Both nebulae are filled with young stars, glowing gas, and sculpted clouds of interstellar material. And Rubin's combination of filters and exposures brings all of that detail into sharp focus. Again, this isn't just a pretty picture. It's a glimpse into how Rubin is going to revolutionize our view of the sky. Astronomers will be able to return to this region hundreds of times, tracking changes, discovering new stars, and watching this dynamic corner of the galaxy evolve. The science potential here, too, is enormous. One of the most exciting things about the Vera Rubin Observatory is it's not going to just show us pretty pictures. It's going to reveal motion. And in one of the most impressive first looks so far, we're already seeing that promise come to life. Let's take a look at Rubin's Swarm of Asteroids sequence. What we're looking at here is a short time lapse, just a little over half an hour of imaging time. But even in that short window, the Rubin team was able to detect and track more than 200 moving objects in the foreground. These are mostly main belt asteroids orbiting between Mars and Jupiter. You'll see them streak across the field as little dots of light, each one following its own path. Now keep in mind, this isn't a processed highlight reel. These detections were made using Rubin's automated software. That's big. Rubin is designed to operate at scale, and this demo shows that the system can pick out hundreds of fast-moving objects in just one patch of sky in real time. And we're seeing only a fraction of Rubin's full capabilities here. This short test was taken using just a part of the telescope's full imaging field. Once Rubin is fully operational, each 15-second exposure will cover 9.6 square degrees of sky. That's more than 40 times the size of the full moon. Multiply that by thousands of exposures per night, and you start to see the scale that we're talking about. One of Rubin's key science goals is to dramatically expand our catalog of near-Earth objects and main belt asteroids, and this video shows exactly how that's going to happen. By taking repeated images of the same region of sky, Rubin will automatically detect, track, and catalog thousands of objects every single night. For planetary defense, solar system science, and even amateur collaboration, this is a game changer. So when we talk about Rubin revolutionizing astronomy, this is what we mean. It's not just looking deeper, it's watching the sky unfold in motion with extreme clarity and precision. If these first images are any indication, the survey data that Rubin is about to start collecting will be nothing short of revolutionary. I'll include a link in the show notes so you can check out those first light images for yourself in full resolution. You don't want to miss them. Now that we've got a sense of just how powerful and revolutionary the Rubin Observatory is, let's talk about what it's actually going to do, because this isn't just about taking pretty pictures of the night sky. It's about using those images to tackle some of the biggest, most fundamental questions in modern astronomy. The Rubin Observatory's flagship mission is the LSST, and over its 10-year run, this survey is going to completely reshape our understanding of the universe in 4 major science areas. Let's walk through them. Let's start with the big one, literally. Roughly 95% of the universe is made up of dark matter and dark energy. We don't know exactly what they are. We can't see them directly, but we know that they're there based on how they affect the motion of galaxies, the structure of the cosmos, and the expansion of space itself. The Rubin Observatory is uniquely suited to help us investigate both. By repeatedly imaging billions of galaxies, Rubin will track how their shapes and positions are distorted over time by gravitational lensing. That's when the light from distant galaxies is bent slightly as it travels through space, warped by massive objects like dark matter halos. By mapping these distortions across the entire sky and over time, Rubin will help us trace where dark matter is and how it's distributed on a universal scale. As for dark energy, that mysterious force driving the accelerated expansion of the universe, Rubin will observe hundreds of thousands of supernovae, which act as standard candles. By measuring how bright they appear versus how far away they are, Rubin will provide one of the most precise measurements ever made of how fast the universe is expanding and how that rate has changed over time. In other words, Rubin is going to give us a 4D map of the structure of the universe. That's 3-dimensional space and time. The second science area of focus is that a lot of people don't realize the sky is not static. Stars explode, asteroids zip by, galaxies collide, and Rubin is going to catch it all in real time. Thanks to its rapid cadence, taking new images of the entire sky every few nights, Rubin will act as a kind of cosmic surveillance system. It'll catch transient events as they happen. Things like supernovae, the explosive deaths of stars which can briefly outshine entire galaxies, gamma ray bursts, intense bursts of energy from dying stars or neutron star collisions, kilonovae, the merger of 2 neutron stars producing heavy elements like gold and platinum, and tidal disruption events, such as when a black hole literally tears a star apart. The observatory will send out real-time alerts, over 10 million per night, to astronomers and observatories around the world, allowing other telescopes to zoom in and study these fleeting cosmic fireworks before they fade away. This alert system means Rubin isn't just doing science, it's enabling other observatories to do their best work too. You could call it a collaboration machine of sorts. Looking a little closer to home, Rubin's third science goal is to help us build the most detailed map of our own galaxy, the Milky Way, that we've ever had. It will catalog billions of stars, measure their brightness and motion, and reveal how they're moving through space. This kind of data will help us understand the structure and history of our galaxy, how it formed, how it evolved, and what kind of remnants have been left behind by past mergers with smaller galaxies. It'll also help us identify rare and fascinating objects like white dwarfs, neutron stars, and brown dwarfs, stellar fossils and failed stars that are hard to find but packed with valuable information. Ultimately, Rubin will help us piece together how the Milky Way became what it is today. Rubin's fourth area of focus will serve as a key part of our planetary defense. The observatory is designed to detect near-Earth objects, or NEOs. These are asteroids and comets that come relatively close to our planet. Rubin's large field of view and frequent imaging schedule make it ideal for spotting new objects and tracking their paths with incredible precision. In fact, Rubin is expected to increase the number of known NEOs by more than a factor of 10. And here's the important part. It will spot many objects that are smaller, but still potentially dangerous, long before they get close enough to pose a threat. That gives scientists and space agencies time to plan and prepare if something were to ever be on a collision course with us. So whether it's unlocking the secrets of dark matter, discovering new stellar explosions, mapping our galaxy, or protecting our planet, the Rubin Observatory isn't just one of the most ambitious astronomical projects of all time. It's also one of the most important. Let's talk data. Because the Rubin Observatory is producing so much information, tens of terabytes per night, it also includes a robust data management system. The data will be processed in near real time, flagged for transient events, and archived for long-term analysis. The observatory's data will be made available to scientists around the world, allowing collaboration, discovery, and participation from across the global astronomical community. There's even a public interface planned for educators, students, and citizen scientists to dig into this incredible data set. So why does all this matter? The Rubin Observatory represents a huge leap in how we study the universe. It brings together cutting-edge hardware, sophisticated data processing, and open science to give us the most comprehensive, dynamic view of the sky that we've ever had from Earth. Whether it's discovering new dwarf planets, refining models of cosmic evolution, or even spotting something completely unexpected, this telescope has the potential to redefine what we know about the cosmos. So the next time you're out under the stars, remember 8,900 feet up in the Andes, the Vera Rubin Observatory is working hard to catalog the sky, track the motions of galaxies, watch stars explode, and unlock the mysteries of the universe, one 3.2 gigapixel image at a time. Together, let's look forward to seeing what this great observatory will discover. Well, thanks for joining me on this episode of the AstroGuy Podcast. If you have questions or want to share your thoughts on the Rubin Observatory, email me at astroguypodcast@gmail.com or leave a voicemail or a text at 973-404-0380. Be sure to check out the AstroGuy Podcast group on Facebook and visit our YouTube channel for past episodes, observing tips, and bonus content. If you found this episode helpful, please like, subscribe, comment, and share. It really helps us to grow. And if you'd like to support the podcast, you can buy us a cup of coffee. Your support helps us keep the mics and computers on and the telescopes pointed skyward. The link is in the show notes. Until next time, may your skies be clear, and as always, Carpe Noctem, seize the night. I'm Zuhl, and this was the AstroGuy Podcast. Thank you for listening. As always, your questions, comments, and suggestions are welcome. Keep wondering. Keep your eyes on the sky. Have fun. Carpe Noctem. Seize the night.